Started here. First talk is going to be Gentle Introduction to GIS by Jason Shire. I certainly hope it's gentle. Just from my personal experience, I was actually doing some open data mapping this last year and realized that I was way out of my league with GIS. So I'm really looking forward to this. So I'm going to turn it over to Jason.
Hi, I'm Jason Shire. I work at Esri, which does all GIS software. I've already got the slides online if you'd like to look at them now, and there's a few links on that page as well. First off, we're going to talk about what this talk is, and basically, I'm not going to talk about web mapping, any web mapping platforms at all. I am a Python developer. I started as a Python developer. I sort of fell into GIS, and so I'm going to talk about the things I wish I'd known. Basically, the terminology, not necessarily the tools, but the theory behind a lot of what's going on in GIS. That took me a long time to figure out, a lot longer than it should have. So first off, GIS is a lot more than just dropping points on a map. I mean, you've got lines, you've got polygons, but then you pan out, you look at the horizon, and you've got some terrain data, you've got three-dimensional data. You can drape some imagery on top of that from a satellite, and now you've got raster data. And you zoom into a building, and you can store all kinds of three-dimensional information as well. This is also useful. 3D information is used a lot underground, too, for things like gas and oil exploration. So I'm going to cut it up into three prongs. I'm going to talk about storage and file formats. I'm going to talk about visualization, and I'm going to talk about analysis. And I'm mostly going to emphasize the visualization because that's the part that's easy to get wrong as a Python developer. That's the part that's kind of the mystery. So first off, storage. You're going to have two major forms of data. You're going to have vector data, lines, polygons, that sort of thing, and you're going to have raster data, which are basically imagery that's plastered on the surface of the Earth. For vector data, the unfortunate thing is that the shapefile is still the major interchange format. The shapefile is a misnomer in that it is actually 3 files, and one of them is a DBF file. It will not die. Other formats are KML, which is XML, but it's easy to distribute. GeoJSON's another nice one that's human readable. SpatialLite is a very specific build of SQLite that includes spatial types. It's a little hard to get up and running, but it's nice when you do. The exact opposite is our proprietary Esri file geodatabase format, which is a closed format, but very easy to get up and running, linked into a C# or a C++ code base. For databases, they're all relational. The ones with spatial types, every big one has it. Bar none, PostGIS is the best option to get started. It's got amazing spatial types. It's got great spatial operators. I recommend you download it, read the documentation, and get started with that as soon as you leave this talk. For raster data, you've got another set of formats. There are a lot more of them. Some of them are more proprietary than others. My favorite is GeoTIFF because it's just got some extra EXIF tags on the image. Other formats that are becoming popular, NetCDF and HDF5 are good for scientific data and raster data sets, a lot of weather. There's an HDF5 talk that overlaps this that you might want to catch the end of if you can. Other versions of raster data for imagery, some have different types of compression levels. Some are basically lossy or lossless depending on the type of data that they deal with. They're usually very large-scale global imagery, so there's quite a bit more proprietary, scary stuff that I don't understand involved in that stuff. GIS data is all completely conventional, and I mean this in it's very boring. GIS data, for the most part, is stored in relational or relational-like store with columns with types, and the only real special thing about it is it's got a column with some geometry on it. I haven't seen anything in the NoSQL world that does much beyond point lookup, so I'm not going to include them. Most of the data you see is going to be in some sort of relational form, even in a shapefile. The constraints aren't, though. In a normal database, you've got some fairly simple constraints. You've got foreign key constraints, you've got an integer that you've got to keep in a certain range, something like that. When you're talking about spatial data, you have more constraints with relationships between the data, between the shapes themselves. So say you've got, instead of a foreign key relationship, every point in your point data must be within a polygon in some other table. Or you've got some land use data, you cannot have slivers of unused land in between each parcel. That is bad. That can cause a lot of legal problems. And so the idea of keeping something spatially integral is called a topology, a topological rule. You want to keep your entire data set clean. And you usually put these rules on your database level. And the tools used for doing data management with file formats in open source are mostly the GDAL project. GDAL is kind of the gold standard for doing rasters. And it's got a sub-project called Ogre for doing vector data. For the most part, you're going to be using the command line tools for doing transformations and conversions and stuff in the open source world. On the ArcGIS stack, they're all geoprocessing tools which are accessible from Python. They're fairly simple. You would probably be calling out to the command line in open source. In the ArcGIS stack, you would be calling out from a Python script. So I was talking about one of those columns is translate and reproject. What are those parts? And this is what the hardest part for me to learn was. First off, let's think of the Earth as a perfect sphere, which it's not. It's kind of weird and oblong, and treating it like a sphere mostly works, but not always. So we're going to, instead of just having a simple circle, we're going to turn it into a three-dimensional ellipse, and we're going to tweak the parameters so that it's a little bit fatter in the middle and a little bit tweaked so that it fits the shape of the Earth a little bit better. And this is called a datum. Say we're looking at these 2 points on Earth. This datum is good enough. It covers the Earth more or less in the correct shape. But on that upper arrow, you'll notice it's a little bit off. If we're only talking about data that is in that upper area where it is a little bit off, then we don't need that precision across the world. We only need it in that one place. So we tweak it to become a local datum. We just change a couple more parameters, and it's more accurate there, but if you look on the other side of the world, it's way further off. So a local datum is only for local data. And you'll see when you zoom in, a datum, regardless of how good it is, regardless of how accurate it is, it does not contain topological information. It does not contain your elevation data. When you get a WGS fix and you giggle because you're at the beach and it tells you you're 40 feet underwater, that is the closest you can get with that mathematical model. The science of measuring the Earth has been around a lot longer than satellites, about as long as trigonometry. It's called geodesy. There are a lot of people who, like surveyors and that sort of thing, who have been around doing this for a very long time, that have very specific scientific methods for doing this stuff that they're good to talk to, but they're a little confusing. So the one datum that you're going to care about the most, the one you're using implicitly with all your spatial data right now, whenever you get a GPS fix, is the WGS 84 datum. This is something you should take away from this talk. When you need to know what spatial reference you're using, you are probably using WGS 84. If you're looking at some government data, something specific to the United States, you're probably using the North American datum. That's one of those tweaked ones that I showed where you push it around a little bit. This one is better for North American data. I mean, the variances are within centimeters usually for various datums, but it's kind of important, again, for like land use or if you're building a skyscraper or something. So again, now that we know how to model mathematically what the world looks like and kind of get an idea of its shape in a very abstract way, how do we talk about the points on that map? So we're going to imagine this perfect sphere. And we're just going to draw a line across it, nice little equator that gives us a point of reference. It's pretty intuitive to know where we are, north or south of this center place. But then we need a prime meridian, and this is abstract. This is completely arbitrary because there is no place on Earth where it makes sense to divide it in half. You can tweak your prime meridian in various map projections, in fact, to recenter the Earth on your area of interest. And now that we've got two axes to talk about a point, we can actually refer to a point. You're usually going to use degrees. You're going to use some sort of radian or degree-based system for referring to it in the context of these two circles that you've drawn around the Earth. And you'll see in a lot of older GIS data, you'll see degree, minute, second. Usually when you have a GPS fix, you're getting it back in decimal degrees. That's probably what we all think of world coordinates in. And then this next one is a UTM zone. This is something special because it's not referring to things in the context of the entire world. We're talking about a grid of meters that we've cut the world up into. So So UTM zone. First, we're going to slice up the world into 6-degree wide sections. We're going to stop at 84 north and 84 south because those wouldn't make any sense. We have different projections for those. Now that we've got it chopped up into areas, you basically take it and you turn it sideways and you've got a projection you can use to minimize distortion. You then, from there, you can cut it up into grids. And these grids have numbers and letters and are kind of weird. But this is your point of reference. Once you've got some data that's local enough to fit in 1 or 2 of these squares, you go ahead and use a UTM grid because you get meters. And when you have meters, you don't have to worry about being 7 or 8 decimal points deep before you get to the relevant part of your coordinate. And as we know, floating point numbers on computers are really bad at remembering anything beyond the first or second digit in a float anyway. So that point we were just looking at, again, it's in P33. It's a certain number of meters east and north. Another way of referring to places on Earth are referential to a specific point. And again, we can use a Cartesian plane here to make math easier rather than the degrees that we used in the WGS datum. And this is the US state plane. The United States is cut up into a bunch of little pieces, and everything in each of those pieces is referred to in reference to an origin point. So it's all Cartesian. You can do 2D math on it, and it works great. Most government data is in some sort of state plane. So again, we've got a system on a beautiful, perfect sphere with reference to using degrees, or not so much on the grid systems, and we fit it to a lumpy, bumpy Earth. So again, we're gonna have different coordinate systems to refer to places on Earth based on how much of the Earth we care about that are more or less accurate locally, but work better in the area of interest that you're talking about your data. So you've got a geographic coordinate system here. And so now we're going to go into the visualization. This is the hard part. This is where we're getting into maps. So here's a map. This is actually using the Esri tiles, but it's the same thing. You can overlay it straight on a Google map, and it's the same tiles. It's the same tiling scheme. It's the same everything. These are just prettier. I like using them. Every map projection is taking you from a coordinate on the surface or at some point near the Earth in reference to 3D space, and you are flattening it onto a piece of paper or a screen. So you are losing a dimension of resolution. So we're going to build up getting a map. First, we're going to start out with some datum or some grid, some way of modeling our area of interest of the Earth. WGS 84 for GPS coordinates, a UTM zone for meters, again, or a state plane, which then we use to refer to places on Earth with our geographic coordinate system. From there, we have our mapping that maps the geographic coordinates to a projected coordinate system, which is what we then use to put things on screen to look at them as a map. There's a big trade-off between every map. Since you are going down to a two-dimensional surface, you can either preserve shape or you can preserve area. Ones that preserve shape may not necessarily preserve the area relative to one another, so you need to be aware of this. Which brings us to our next slide, which is a little bit hyperbolic, but it's true. Every map is a liar. Every map you look at is lying to you in some way. It is misleading you in some way, and it is necessary to know how it is lying to you and how you can make your maps lie less. So again, I'm just going to outline all the major land masses, and I'm going to take 2 of them. I'm going to take Africa, and I'm going to take Greenland. I'm going to put them on top of each other. You'll notice we're using the Web Mercator. This is what we see in all our web maps. I'm going to put them on top of each other, and they're about the same size. But what if I had a globe in front of me, and I was just looking straight at the globe onto Africa, and then I tilted around and I looked straight down on Greenland? This is what I get. My map has lied to me, and I didn't even know it. And this is sort of rampant in a lot of what we see. And on a web map, a perfect 1 kilometer by 1 kilometer square somewhere up in Greenland is going to be a little bit stretchy, and it's important to know that. So again, here's another projection I like. This is the U.S. National Atlas. You'll see there are curves on it because it tries to preserve area and shape for a smaller region than the Earth, but it's still not super great. So now we're going to look at lines. I've just got another web map open here, and I'm just drawing a line from 2 points. All right. Now I'm going to reproject it in something that looks kind of 3D, kind of like a globe. It's kind of a fun projection to look at. You can pretend you're using a 3D program. And, it gives you a better idea of how everything relates to itself, shape-wise. But that last line I drew goes across these coordinates, not the ones I'm looking at here. So even a straight line is not necessarily a straight line on a map. So we'll go back to this projection, and on that mappy-looking one, that 3D cool-looking one, that straight line that was straight on the 3D map looks like a curve now. So which one is right? Nope, neither of them. Just because it was 3D doesn't mean it was telling the truth. What you need is a great circle line. And what you usually do is, since most mapping doesn't draw a straight line that's a correct straight line as a curve, is you're just going to put some points in the middle of it so that it'll render it in such a way as to look like a curve. And you'll notice on that top line I did it with just 6 or 7 points in the middle, so you can tell I'm doing that. But in the other ones, in that middle one, I've done like 15 or so. So I'm lying to you in that it's not actually a single line, it's a bunch of lines. So the PyProj project actually had a really nice function. I was surprised to see how easy it was to do. So I created a WGS84 ellipsoid, and then I just get a number of points in between. And for this example, we're doing 12 points. This doesn't include the start and end. And in ArcGIS, it's a little bit more work because there's no dedicated function to do it. The big thing is in that middle section using the position along line operator on a line geometry to get more lines that you can use to densify your polygon, or your line. So again, we're going to look at a map from, this is a reproduction of a map that was in a major magazine recently about the missile range of certain North Korean missiles. It looks kind of scary, those one orange missiles can go through half the United States and pretty much all of Europe. It's kind of weird, but just because these ranges are perfect circles doesn't mean that we're being told the truth. Again, this map is lying to us, and we don't realize it because, we think of ranges as perfect circles. And this map has perfect circles on it. What they would actually look like if it took the shape of the Earth into account, if it took a geographic coordinate system into account rather than just numbers on a screen, is this. So you can imagine, you've just lied with a map on accident. It looked fine. But can you imagine delivering that first map to a leader of some sort who's making international policy decisions based on the information you've given them that is incorrect? So it's important to know these things. And always take geodesy into account. Switch to a non-projected coordinate system when you can. There are a lot of tools to help you with that. But do not just go by those decimal numbers that you get from a GPS fix. Don't buffer by that. How long is a single decimal degree on a GPS fix? What's the distance? There is none. It's arbitrary. It changes from north to south and east to west. Depending on where you are, 1 degree of latitude or longitude is a different length of real measure. And then from there we can go into analysis. We've built up a system that we can understand the Earth about by first getting an idea of how the Earth is shaped. First we're going to have a grid. We're going to get an idea of what either the whole Earth looks like, or we're just going to go relative to a point in meters. And then we're going to go ahead and put it on screen by reducing 1 degree of resolution, going from 3D to 2-dimensional, and we can look at our coordinates. With analysis, you're just doing stuff with spatial data. You don't have to worry about the projection. You usually throw it away and go back to geographic. 2 really well-defined problems that you will see a lot are geocoding, which, if you generalize it out far enough, is just mapping text to space, and network analysis, which has 2 different flavors. The one you're most used to is probably getting driving directions, where you're an independent agent working through a graph data set. The other one measures overall holistic flow in a graph data set or a network. For example, if there's a windstorm and a power line goes down, how many houses are going to be affected? If I've got this water pipe and it has this capacity, how many more mains can I branch off of it before it becomes dangerously low flow, things like that. And then we get into just bread and butter spatial analysis, where we do relational and topological operators. This is where you piece together your own tools, your own analysis with some basic tools that are provided in open source and in the ArcGIS stack. So the relational operators, they just take two geometries and they will return true or false. The one you probably care about most is point and polygon, which is intersects, which doesn't exist, at least in the traditional definition. So what you really want to use is the disjoint operator. You want to use not disjoint. You want to use the opposite of the disjoint operator to figure out what points are in your polygons. This also applies to Postgres. Topological operators take two geometries and they will do something relative with them. Usually, for the most part, it's stuff you do with Venn diagrams plus a little bit of extra cool stuff. So you've got your two polygons. You can do a union. You can get them both together. You can do a subtraction. You just get the difference between the one. You can do an intersection. You can do a symmetric difference. You can do a convex hull, which finds the minimum bounding geometry of a group of geometries. And then there's the buffer, which is the fun one. And again, it's fairly easy to do with the tools provided. I wasn't able to do this in a spatial reference agnostic way in Fiona, unfortunately, so I didn't post it. But for the most part, you know, if you're doing just simple point and polygon, you probably want to do something within a distance. So you will buffer your points, and then you'll find which points intersect it. And so, well, a lot of spatial data is on the web. You still have to use the desktop, for the most part, to do some processing and analysis of it. There are two desktop suites available, one open source. Well, there are a lot available, but the two that support Python well are one, Quantum GIS, which is open source. You'll see a nice little Python prompt down there, and you can open maps and open PostGIS and shapefiles and that sort of thing. And then there's the ArcGIS suite with the desktop, which also has a nice little Python prompt and lets you do pretty much all the same things and quite a bit more. And I ran quite a bit early, but I have to say, from the point of view of a Python developer learning spatial, I think the most important part is learning the idea of the coordinate system, learning the idea that you don't just have these numbers from negative 180 to 180 and negative 90 to 90. There's something underlying that. There's a theoretical underpinning that you need to understand and need to be able to translate into something more appropriate, especially if you're doing something like a buffer, you're finding your closest neighbors, that sort of thing. And that math is mostly implemented in C++ and C, so you're going to probably be using a lot of open source CPython extensions to do this. There are slowly becoming more and more pure Python implementations of these things. And I mean, that's good, but for the most part, you're going to be using probably PyProj, Shapely on the open source side, and then there's a new one called Fiona for doing actual analysis and not just doing spatial relationships. And then on the ArcGIS stack, it's just sort of all baked in. So again, all the slides are online with some links on that first link, and there is also a dedicated Stack Exchange to GIS. I recommend you visit that and just read all the most favorited and most viewed posts to get a little bit more of an idea of what's going on. Python is kind of the de facto language for GIS, the same way that it's kind of taken over scientific computing, but quite a bit more so. So as a Python developer, you already are 90% of the way there to being a good GIS developer. It's just a matter of building that fundamental understanding of the way that spatial data works and applying it. So thank you.
So when you were showing the Cartesian map of the U.S. states, I was wondering where those divisions came from. Are they corresponding to like different altitudes? Apologies.
You'll notice, go back to it. You'll notice that they're largely just either very long east-west or very long north-south coordinates. They're fairly arbitrary. They were based on a survey from the 1930s to cut up the Earth, to cut up the United States into regions. They're arbitrary for the most part. They try to avoid major metro areas, and they tend to be very far either east-west or north-south to minimize distortion because they all have a specific projection that they go along with as well.
Well, I have a question. I mean, not being so familiar with the GIS side of Python, I mean, how much interaction have they had with sort of the scientific computing crowd? Because I was in the IPython tutorial the other day, and I was saying, man, this would be really interesting if you could do mapping in like IPython notebook or something. Do you know whether anything's going on with that?
Other scientific computing, yes, there actually is a project, third-party optional add-on to Matplotlib that will let you draw maps and a few coordinates, so you can just throw your spatial data in straight from that way. And again, on the GIS side, for raster data especially, it's a natural fit for NumPy arrays, and the ArcGIS stack supports it, and I believe that some of the open source stuff is catching up as well. Because, I mean, they go together very well. GIS is basically just a very specific flavor of scientific computing, and there's a little bit of isolation because it's not necessarily the same scientific community, but yes, there is quite a bit of overlap, and you can do maps pretty easily in Matplotlib and in IPython. I use IPython pretty much exclusively at work, as in the other direction.
Okay. Do we have any more questions? Okay, thank you very much. That was great. Oh, wait. Okay, wait. Okay. Don't want to jump the gun.
Could you explain real quick the North Korean map again? I wasn't completely sure if the shaded regions was where they can...
Yeah. So basically, we're building a buffer of a certain distance around North Korea. So we want just the range within, I think it's 6,000 and 10,000 miles. I don't remember the numbers. It looks right here because you would imagine a range to be a circle. But there's distortion on this map because it is a Mercator projection. It is not necessarily what the surface of the Earth looks like. This is what it would look like if it were correct. And we can play around with some projections to kind of give you an idea of what you can do with this stuff. Close some of this stuff out. So this is the web Mercator projection. Actually, this is what you usually see on a web map. Kind of the implicit projection that you see in Google Maps or whatever. But you can play around with projections actually here. If we pick another one that might be a little bit better, you know, you've probably seen projections like this where they try to maintain the curvature of the Earth. You've probably seen this one in your textbooks here. Wait for it to finish rendering, but you've probably seen these. There are a lot of different projections. You're losing some sort of spatial data. You're losing some sort of information in the relationship between these shapes on a three-dimensional surface whenever you flatten it onto a map. So yeah, you can also get crazy stuff like the Fuller projection that programmers... which equidistant one? I will do a conic. So this one, a line in any length is the same distance from the point of origin. So this map, it actually would be a circle? This map, it actually would be a circle, yes. Well, if the center of the map, if it's centered, otherwise it would be distorted, correct? So you usually go with a conic projection system where you're looking at a single point. Basically, you've got a cylindrical projection where you're just cutting a seam in the Earth at some prime meridian and flattening it out. You're basically cutting down the center of an orange peel, and you're slamming it down onto a piece of paper so that it's flat. Other ones are conic projections where you're basically looking down at the orange, and you cut off half of the orange and just stick it down on a piece of paper, and you just look at it as half the Earth, just straight down at it.
Can you truly do this conic projection off of North Korea?
I couldn't do it easily right now, no. I'd have to...
That might be a neat way to do it.
Yeah, that would be a good way. But it's just amazing how much we take maps for granted and how little we know about them, really. So...
I have a question.
Yes.
How come the Fuller projection's crazy?
Remember Buckminster Fuller with all his geodesic junk?
I know tons about him. I'm from his institute, actually.
Okay.
So
it's just very confusing because the way that it...
Why don't you put it up there so I can take a picture and send it back to my
It's
Facebook
obviously a
post.
very interesting...
I'll Twitter this. It's a really good map because it's not distorted compared to
It's
the
not
others.
distorted, correct.
We always call the other people's maps crazy, so I'm interested to come to your world.
It's just very non-conventional.
Well,
And
very, very, but it folds up into a polyhedron, so that's cute.
Yeah,
So-
it's really cool because you can fold it up. It's really mathematically interesting. It's
And Esri has it, and we're very pleased about that.
Yes,
You should know.
yes.
You should get marketing kudos for that.
yeah, I mean it's really cool to look at. It's just hard to communicate data effectively to a non-expert.
It's also good for showing how missiles go because they
Yeah.
will go north-south more
Yeah.
than east-west.
Well, yeah, that's another good point. You
Yeah.
can see
It's
how
a very good Cold War map. That's what's
Yeah.
good for that. Yeah.
I suppose so because you're going from I'm too far away here, but yeah, you're going from like Pyongyang to Seattle. You can see the relationship quite a bit better with this map. Yes.
You had those 2 slides with all the operators.
Yes.
Do you think we could take a couple minutes to go over each one briefly,
Sure.
since we have a bunch of time?
Those are further down, huh? Sure. So yeah, contains. It's. I was talking about disjoint because that includes if it's on the line or within the shape. Contains means it has to be completely within. Crosses is for 2 lines basically. If the 2 lines touch each other but they don't overlap. Disjoint is again if they have nothing in common whatsoever. Equals, same thing. Overlaps, basically 2 polygons or 2 lines that just sort of Venn diagram over each other. Touches, again, is one of those things where like you've got a point right on the edge of a line or a polygon, or you've got like a line that goes along the edge of another line on a polygon, something like that. And then within, is again another completely contains. And then the topological ones are a little bit more. These ones give you back geometries. The other ones give you back true/false. So these ones with the geometries are the more interesting spatial ones, where you can actually see what's going on. It's not just a test of true or false, but you're getting back a new geometry from doing something to these geometries. And the slides are online, and I think I included a link to some ArcGIS help that explains this a little bit better than I can.
I used GDOL on the command line, and I know there's Python lines out there.
Yes.
What does it get you with a Python line beyond what you can do with a command line? Is it full access to their model of the world or the data set?
What's the exact advantage of using the Python GDOL bindings? Basically, yeah, you do get the full API implementation, the full object model that you can talk to through Python. So if you're doing something in Python, that's something you probably want to do. The Ogre project, for the vector data, Sean, who was our runner, actually implemented a really nice wrapper for called Shapely. And he's also done some really nice work. He just recently released a version of a library called Fiona for doing cursors on spatial data as well. So that might be something to look into too, is to evaluate spatial data. Any more questions? Okay.
Okay, thank you very much.
Thanks.